commits yet. And usually, I'm so used to the newer versions. So if it's not ready, let's troubleshoot this really quick. Gcloud, and I think this is my own Easter egg. We want to do list all of our nodes, so compute list instances list. So we're going to list all of our instances, and one thing I'm going to do for a troubleshooting perspective, the API server needs to be able to hit these things by its resolvable IP address. So we'll log into it really quick. So I'm going to log into the API server. So from the API server, I'm just going to simply try to ping this endpoint. So good, it's resolvable, right? So that's good. That's first step to know that this thing can actually communicate to the other side. So now what I'll do is I'll come out of this, and maybe I wasn't patient enough. It's still not ready. So what we can do now is go to the other machine, and I think the issue here is that it timed out talking to Docker, and it didn't heal itself. This thing is about 2 versions back, and that's been fixed in later versions, but I'm pretty sure that this thing is just stalled out trying to connect to Docker. I'm going to verify it really quick. So I jump on to the API or to the kubelet. So I'm on a kubelet now. And since all this stuff was started with systemd, I can basically look at the systemd journal to see if there's anything going wrong here. So I'll do kubelet. So it looks like a dependency failed here. A hard dependency failed. So let's just restart this thing really quick. Sudo systemctl restart kube. All right, and let's see if we're back up. So this thing is coming back up. It's trying to refresh itself. It's going to talk to the API server now and say, look, I have this host name. I'm just going to start giving you status updates. I assume someone's going to register me, or I'm going to register myself. And it's just sending these periodic updates about its resources, its host name, and it just assumes there's a key that will be online. So right now it says that it's online. So if I've restarted it, and we come back out here, and we do get nodes, and it's ready. Right? So this node is now ready to be scheduled. If there's any issues, the node will just be in a state where it's like, don't send me anything because I don't know the health of myself. I'm going to add another node, and let's see if it should be healthy. We'll add another node. It doesn't matter what the name of this thing is. An idea would be you just let these nodes manage themselves, and they just register themselves automatically. They do generate their own tokens and talk over a secure channel. But if you really want to be serious, you delete all the automatic certs, and you give each of them a cert. That would probably be a bit tedious if you don't have good automation tools to handle it. So we'll do kubectl create -f node 1 again. So we'll get this other endpoint. Let's see if we have better luck as far as it being ready. So we're unknown here. And I don't know, maybe I have the same issue on that machine. All right, that one's ready, right? So it came up, everything was good to go. Now that we're up and ready, let's start scheduling things. We have 2 nodes. If we run out of capacity, we'll spin up some more nodes. So at this point, we've gone through setting up a node. Now if we describe these nodes, now they're registered with the system, so let's describe one more of these nodes. We'll see the rest of the information comes from the system itself. So this is an older version. It doesn't show the memory and CPU, but actually all of that's actually captured in the system now. And it tells me the CoreOS version that we're running, the Docker version, what version from Git that we have, and any of events that we have. So you notice when that thing came online, an event landed into the system. You can watch for these events and do whatever you want with them. Maybe you want to start a billing process when these things come up. There's so many things you can do with these event systems that you can watch on the API server. So now we have more data about the particular node. Again, later versions say they have the CPU. Oh, there it is, sorry. Here it is, CPU and memory. All that comes from CAdvisor. So CAdvisor is collecting these metrics and constantly updating them here. All right, so now that we have our nodes online, we can start scheduling things. So next step in the tutorial, looks like we're going to finish on time, and we'll have time to do more complex setups. Where's our tutorial? Here we go. Did I close that page? Right, so the next thing we need to do is we're going to launch pods. So now that we actually have nodes that are schedulable, they're in a ready state, we can actually start scheduling things to this. So I'm going to check out these configs, this intro to Kubernetes. I think I already have them out. So here's my intro to Kubernetes folder. You can select that down via git. And then you can list your pods with the git pods command. All right, so there's no pods in the system. Now we want to run a pod. So we'll look at the hello pod really quick. So underneath the Kubernetes configs, we'll just go in that directory and make it easy. So here's a hello pod. So this pod will have an environment flag called testing, name hello, and right now I'm only using one container, and it's going to get this hello pod from Quay.io, right? And there's some policies. So if it's already there, do not attempt to pull at all from the hub or anywhere else. And you can use DNS. So if we have our DNS add-on, it will basically allow you to reference the other pods by a DNS convention or services by another DNS convention based on you having that enabled. So let's create this pod. So kubectl create -f. Make sure we're doing the right pod. We'll do the hello pod. All right, so now what's happening is it got pushed to the API server. Now the scheduler has this in the view. It's not running on any pods right now. Scheduler takes hold, and it should find a place for it. So kubectl get pods, and we found a home already. It landed on this node, testing kube 0, right? And the pod IP is this, and that comes from that Docker bridge that we set up. So in each of these machines, Flannel is managing the Docker bridge. And Flannel talks to etcd to get this initial config to say, hey, here's the subnet that I'm going to configure each machine with, and it works kind of like DHCP for subnets. So this landed on that machine, and it got .2. Now, if we log on to this machine, we're going to see the IP table stuff that actually happens here. So we can get a full view of what's going on. All right, so we're going to log into the machine that it got scheduled to. And let's node this guy. So we'll log in. And then we're going to talk about that infrastructure pod, right? So what happens is if we do docker ps, you see this pause container, right? And that's all it does is just sit there and just pause and blocks. It's the thing that gets assigned the IP address. And this holds the IP, and this other container is joined to the network namespace of the other pod, right? And the kubelet handles the linking and locking of the lifecycle between them. So if you delete that pod, it will delete those two containers that go with it. Now, on the networking side, remember we have one service in the system already. So if we look at IP tables, and we'll do, let's just do -n here. And it's going to be the NAT table. So the table is going to be the NAT table. So if you look here, and the important bits are down here. So you notice Kubernetes, the kubelet, makes its own chains inside of IP tables, right? So here's the portal container. It does some redirects to get to the actual proxy itself. But notice here, so what we do is we got a portal VIP for the API server, and it puts a little comment in here. So for the read-write API endpoint, we got this IP address here allocated for us. We don't do anything on a network interface. We just do this in IP table. So when someone sends a packet to this particular machine, or a local container tries to make a call to that destination, what will happen is it will be intercepted by IP tables and forwarded to the Go binary running as a proxy server. It will then do a label query to find the API server and have the IP and forward it to where it's actually running in the system. So that's how that works. And as you add more services, that Go binary that's acting as a proxy, it will be the one doing these things. And you can kind of see the whole proxy thing that it's doing. So it's actually binding to a port so that actually all works. And you just have to have these forwarding rules put in place. That's all managed by the proxy server. You turn the proxy server off, you don't get the IP tables rules, and you can do something different if you wanted to. But it'll be your responsibility to follow the services. That's all that happens with the kubelet. We put a pod in place, sets up the infrastructure pod, one or more containers linked together. That's all the things that happen behind the scenes. And then going on forward, its job is to keep it running and reporting status upstream about the life of the pod and the life of itself, the kubelet.
So when you're sending data like from one the other, it's actually going through the proxy server, or is it?
Yes, yes. And this is why some people turn it off, right? It's like, I don't want the proxy. I just want to go full speed without going through this other thing that's in user space proxying my traffic. It sounds like a big deal, but most people do this already. A lot of people are doing this with HA proxy or Nginx and some of their clusters. So you're already kind of doing this hop, right? But some people have a pattern where they have every service has the ability to know about every other instance of a service that they care about, and they just do more of a point-to-point thing. And they have their own strategic algorithm of like, I want to go to I prefer these nodes because the network latency is lower, right? And this may be something that you want the app to handle. Maybe you do it through a library so it's consistent across your application stack. So you have both models. The easy mode, so this is like easy mode, right? Like, how do I find other things in my network? Well, you have DNS and these environment variables that just help you decouple from how to do that, right? You don't think about etcd, you don't think about registration sidecar patterns and all that stuff. That just goes away.
It's not just finding the other service, it's also like when you're sending the data, right? You're also paying the hit.
Well, you're gonna pay the hit. So, and usually if you have a service proxy up, so you got north-south traffic, you're gonna go up, hit some proxy, and it's gonna come back down. Usually gonna pay a hit, right? Like, this is really hard to say I'm gonna pay 0 hit to find something if you have a service registry in the middle. Or you can just do your own label queries. So inside your code, you're like, you know what? If I need to talk to the API server, I'm just gonna do, man, that's gonna be tough because you don't know what the API server is, so I'm gonna have to configure it, right? Now you're kind of hard coding it yourself. But for the other services in the cluster, and you know where the service locator is, guess what? You gotta pay a hop to discover. So normally with discovery, you're gonna pay one network hop to discover. It's really hard to get away from.
Well, that's okay. I think I'm fine paying a hop to discover. It's just like once you have like your destination, rather than like when you're sending traffic.
Right, so the easy mode would be to have something that can do it for you, so you don't need to do this in your app. Some people are like, I don't want to write new code, right? I just want to use the system, and then the proxy is there for you can use the system. In your world, you would say, no, I'll just do my own discovery because I don't want to pay the hop, right? Or you can use DNS. So when you also create a service, and in our pod manifest, we can say prefer the cluster DNS. When the pod is spun up, not only do you get the resolve.conf that Docker normally puts in there, we'll put the one for Kubernetes in there and be preferred. So if you agree on a DNS name for your thing, you get that, and they added service records as well. So you can ask for an SRV record from that DNS entry and get a list of the pods and do what you want to do with it. So you have options. But easy mode for people that don't want to think about that thing, it's there, but you're right, that's the right question to ask when you think in terms of paying that hop cost. All right, so that's pods. So now, that's pretty easy. We got the pods going. Yes, I'm going to delete this pod. Oh, getting traffic to pods. This is the most complicated thing that you're going to run into with Kubernetes. All this stuff is on this underlay network. You can't hit it directly at all. Can't get into this cluster from the outside. So what happens is, we're going to log back into that machine. This is where most people just give up on Kubernetes 100%, because if we look at this, okay. So right now, the IP that we have from Docker right now is only bound to this guy. And the only way we can get to the address, we need to be actually on the Flannel network. My laptop isn't on the Flannel network. We have no way of getting to this particular pod from outside the cluster. Now, depending on how advanced your cloud provider is, you can do things like routes. So what will happen is you would say, this is the Docker bridge. So the subnet here is 10.10.74/24. Anything in this range needs to go to this particular host, right? If you want to talk to the pod that came up on 79.2, you need to go to this host first. So then in the routing context, that would be, the next hop would be that IP, right? So if I'm on machine B over here, and I want to talk to that pod we just spun up that has a .2, I have no way of knowing about it. GCE has no way of knowing about it. It's not even a real thing that's bound to anything. How do I get to it if it's behind a Docker bridge on the other system? Well, we're using an overlay network, but normally what you would end up doing is say, I need a routing table entry that would do this for me. And the routing table entry will say, well, anything destined for this /24, just go to this other host, and it will figure it out. Because it actually knows how to deal with it because the bridge is there and there's a route entry on it. So we look at this netstat-rn. Here's the route table, right? Anything going here, go to the Docker bridge. So if I can just get the packet to this machine, it will look at this routing table and say, oh, Docker bridge has it, and push the packet along. Now we try to ease this whole thing with Flannel. So Flannel manages for us. So Flannel will come in and say, I'm going to intercept anything going to /16, and I know where the next hop is. And it will do encapsulation. It will basically redo the packet, put the destination header there, go to the other side, where Flannel is waiting on the other side, that will unwrap this thing and put it on the Docker bridge for the containers to talk. Everyone gets confused by this one. And then how do you get traffic from the outside world into the cluster? And this is where the services help us. So if you have routing, then you can just, hey, the next hop for these subnets go there. And so if you have a load balancer at the top and a request comes in on a public IP address and you have one of these pods as a backend, it can just go through the normal routing process and say, oh, I'm going to .2. I don't know where that is. I'm going to go to the default gateway. Inside of most environments, your default gateway knows how to deal with the routes. If you have a route entry, the default gateway will say, oh, the next hop is this machine over here, where we'll find the Docker bridge and will work. A lot of people forgot about routing, so this all seems like magic. But the thing is, this is just how the whole internet works. Seriously, like, most people just give up because they think that this is actually broken. It's actually to your benefit to have layer 3 without, so you talk about hops. When we start going all these overlays, it gets really, really bad, right? So we go through a virtual Ethernet, we go through a Docker bridge, we go through Docker's TCP proxy, we go through Flannel, it goes through some UDP thing, then it hits the wire, and it goes back through the whole thing just to talk to another thing on the other side. It's crazy how much you lose with that for the simple ease of use. It doesn't make any sense, actually. The easier thing to do is put a route entry at the gateway, and then as you go out, it will say that's where you go and you're done, right? It's much simpler to do it this way. So I try to teach people, just learn a little bit about layer 3, and then all this stuff starts to make sense. And you really embarrass your whole team if you go to production without knowing this, because you're gonna, like, doing fine before, and then your traffic's gonna drop maybe by 30, 40% because it's going through too many of these layers. And it's really, really slow. You have to learn about layer 3 for some of this stuff. Flannel tries to help you. So Flannel can run in a mode where it's in gateway mode, and it will manage these routes for you. So we built Flannel just for this very purpose. We give Flannel the whole subnet. It carves it up to each host as it spins up by talking to etcd, and it will update these route entries on the host itself for you. So, and then it will give you layer 3, and then it gets out of the way. We call that Flannel being out of the data path. Because now Flannel's like, I won't do any encapsulation. You want to talk to the other side? The route's on the server. Linux will do the normal routing for you. These are important concepts to know so that way you don't get stuck. Now, how do we get things to the host? I'm going to do it properly, and we're going to use a service. The service is going to allow us to get traffic into the host. It's the right way of getting traffic to the host. You could do some weird stuff like say, you know what, I don't care about port collisions. You will care, but you can say you don't care. And when you don't care, what you can do is like when you create your pod, you can say, you know what, I want no port 80 on my pod. Sweet. It's going to create an IP tables entry to say anything that comes to port 80 goes to your solo pod. And then your developer friend is going to be like, you know what, I want port 80 too. I like port 80. And it's going to be like, all right, sweet. The first role goes to your friend's pod. And you're all hitting port 80 on the host, and it's going to your friend's pod. And you're going to run in circles, right? Because you've never seen IP tables before. And you're going to reboot the box, and you're going to reprovision the server, you're going to do all these things. You're going to have a war room meeting. You're going to put Nagios in place. And it's going to be none of those problems. And the problem comes from you doing this port conflict. And most people, how do people resolve port conflicts traditionally? That's the world's most known database. You get your admins, and they get the spreadsheet, and it's all right, you get port number blah, right? And you got to keep that thing up to date. And then this is how people are doing this. And this is like really, really, really hard to maintain long term. Small scale is probably still cool to do it. But man, just let's get away from it. So I'm not going to even show you how to do it the bad way. You can do it the bad way. I used to show people, and I saw them on RSC, and it's like, hey man, what the hell's happening? I was like, damn it, I showed you. It's my fault. So I'm not going to show you guys. We're going to do this the right way, right? All right, so we're going to delete this pod. And we're at the point where we're almost showing everything that Kubernetes is pretty much capable of. Like all the things that you guys are seeing at a very low level. And once you understand them, you're going to start thinking of new patterns. I've seen people just do some amazing ideas of like, wouldn't it be cool if I schedule a pod, but it doesn't do anything until someone clicks yes on a Jira ticket, and then it talks to Jira, and then it goes. And then when it gets scheduled, it updates the Jira ticket. Now, this is like some enterprise workflow stuff here. But you start to have this imagination that I can actually be in full control of the life cycle of things moving within the cluster, because now I have full view without SSHing to the machines to do stuff. So now I'm going to show you the right way of dealing with services. So now that pod's gone, we're going to move to the next step. here's where labels kick in. So what we're going to do is we're going to do a replication controller. So we're going to talk about auto-scaling a little bit, and then we're going to put a service on top so we can actually find those things. And then we're going to manipulate that service to give me something that only works within the cluster. We're going to add public IP so it works outside the cluster. And then we're going to open up some firewall rules to make sure we can actually move traffic around. And then we'll actually probably get to the point where we do a rolling update so we can see how those patterns work as well. So now what we're going to do is we're going to create a replication controller. This is our auto-scale group. We have no replication controllers. We have no pods. And I'll give people a 15-minute break as soon as we're done with the next two sections, and then we'll go and end on the rolling update patterns. So here's a controller. So the controller looks like this. So the object here we're describing is a controller, not a pod. And what we're saying with the controller is that, look, we want you to monitor the full state of the cluster and be responsible for what? Well, I want you to be responsible for this particular specification. I want you to manage it, starting out with one replica of these pods using this template. Now, the things I want you to pay attention to, I don't want you to watch every pod in my cluster because that's like none of your business. I want you to only care about pods that have at least these 4 labels. If it has 6 labels and these 4 match, you need to worry about it. This is your job. And then when you need to create some pods, I want you to do it with this label or with this metadata or this spec down here. So I want you to create the pod and give it at least these 4 labels, right? Someone can go add labels out of band, but I don't care. You need to create pods with those 4 labels. And then I want you to spin this pod up with this one container inside. So we're going from pod, which is unmanaged. You schedule a pod, you're on your own. If it dies, too bad. It's dead and not my fault. It's gone. Most of the time, that's not what you want. You want someone to make sure that it stays around. So if I unplug the node, it gets rescheduled somewhere else. And the controller is the thing that allows us to do it. So remember, the kubelet can never say, hey, man, scheduler, go reschedule this thing. It doesn't know anything about how to do that. Replication controller can orchestrate that particular flow. So we'll go ahead and create this now. So and remember, this it's the same consistent thing. You're like create, you give it a file, and we're going to create the stable controller. So we're going to do v1. So now we have this replication controller in place. So now we can say kubectl get rc for short. So we have this replication controller. And it gives you a little bit of information about the replica and what its job will be to do. Let me describe this controller. It has this name. So information about it. Sorry about those warning messages. Those are cleaned up later on. But it just tells you a little bit of data about that particular controller. So you can imagine the UIs that will get built around this stuff. Right? So it's going to be responsible for this image or images, because it can be more than one pod. Here's the selector for it. Here's the labels. And it's telling me my current state and desired. So actually, it already got up and running. It already created the pod and went through the schedule process. And it tells you the pod status. So the pod status is that it's running right now. Some could have failed, and it will go through and try to make current, desired, and running all match, wherever that means. Rescheduling until we find a home for everyone. But we'll eventually make it happen. And then we'll get some events. We first sing this thing into the system. It created those bits. And then UIs can stream those events and kind of give you some real-time feedback on some of this stuff. All right? So now we look at our pods, we'll see the pod in place. All right, so this landed on kube 0. It's up and running. It's good to go. So now we want to rescale it. We're going to resize it now. So what we can do here is I want to go from 1 to 3, right? And let's make sure, so let's go to 1 and 3. So now we're resized, and we get pods, and now they're up. So it's going to try to find homes for these guys. So let's see where we land up. It looks like they're going all to the same one. I want to see them go somewhere else. Let's do, what number should we do? 18. I don't know if that'll work. Let's just try it. Because I want to crash the cluster. All right, so we should have 18 at some point. I don't know if that's going to work. Right, so I don't know. These things are coming up. All right, look, some of them are going to testing 1. Some of them are, all right, so they're being spread around. All right, so we have 18 of these things. Who cares? They're all running somewhere in the cluster, and eventually they'll get to the right status and state. So we do a description on that again, see where we're at. So all these events are flying in. All right, so we wanted 18, we have 18 running, and they're spread across the cluster somehow. We have enough resources. If we didn't, and we saw stuff pending, we need to register some more nodes so that way the replication controller can do its job. So now we have 18 running in the cluster, and I still can't get to any of them. So now let's add a proxy so we can have an endpoint that will expose this outside the cluster and handle the round robining for us. If we were to put this behind a load balancer, we could just put all of our nodes in the cluster and allow routing to take place or expose ports to take place. So let's see if we can do that now. So we have a bunch of pods running. And what we want to do, I'm going to delete it. Let's go ahead and add a service. So we're done with that part. Things are scaled, but now I need to get to the cluster. So we do that with a service. So what we need to do now is create a new service. So I'm going to remind people of what we currently have. We have those 2 bits. So what we do now is, let's just check out the hello service. All right, so things you need to notice about the hello service, that it only cares about 2 labels. And the reason why I'm only doing 2 and not all 4 is so I can be flexible. If I want to do a canary pattern where I roll in a new version into prod that's also hello, but the version's different, this is going to pick up both sets and give them traffic evenly. If I was too restrictive, it would only go in one direction, right? But you can get creative and have multiple services. So if you want, or 3 of them, where one is like given to all, one is pinned here, and one is pinned there. And they can all just work in harmony with different VIPs that you allocate to DNS. So here's our selector. I'm leaving public IPs empty. And this means that we're going to get the same behavior where I get this proxy. If you come into the VIP that it gets allocated, that's what you get. So let's just create it and see what this does for us. So kubectl create-f hello service. So we create this service. So what happens now, I didn't specify a public IP. Not this range of public IP. It's like a cluster IP. They renamed it. So it's going to allocate one for me from that pool. So we do kubectl get services. It's like, all right, you know what? You get 10.200.247.17. So that's your VIP now, right? Now, that subnet is no way I can get to it from outside, but it works inside the cluster. So if you wanted to talk to any of those pods, any of those 18 pods, you can log into the machine, and it should work for you, right? So let's log into this machine, and I should be able to do curl, and I get hello, right? Doesn't matter where you are in the cluster. If there was 1,000 nodes in the cluster, and all those pods are only running on those 2, doesn't matter. Any of those 1,000, the proxy is going to put you in the right place. So this is an easy way of interacting with these things. And remember, since this VIP is not tied to an interface here, a lot of interfaces, it's tied to IP tables rules and inspection. So now I can let that VIP live forever and not have to worry about reconfiguring things. All right? So that's how you get that's how you get traffic inside the cluster. But we got to solve our problem here. So our problem that we want to do is, I'm just going to not do the firewall part yet. Well, I'll do it. So I want to allow, what I want to do now is I want to open up the firewall rule to allow traffic into port 80, because that's what I'm going to bind. And we'll see if it's in place already. I think it probably is already. We'll see. All right, whatever. We're good. That's called confirmation, not error. Confirmed is what it should say. So what I'm going to do now is we're going to fix the fact that I can't get to that IP address. And one way I'm going to do it, and there's multiple ways of doing it. One would be to create a service with a thing called node port. But I don't want to show you that because you're going to have port collisions. Now, Kubernetes tries to make it easy to reduce the number of port collisions you can have. So when we create this service, hello service, you can use a type here. And you can say the type is node port. And when you say that, when the Kubernetes API server comes up for the first time, you can give it a range of ports that you wanted to use to dynamically allocate to these machines. And that port will be bound to the actual host itself. So by default, that'd be like port 38,000 something. So then for the hello service, on all the machines, if you hit port 38,000, you're going to go through the proxy, and it will work. You're going to do that until you run out of the range. Another way of doing it is by using public IPs. So public IPs is a way for us to declare that, you know what, I only want these 3 machines. If you hit them, they're the only ones allowed to proxy for that particular service. So what I'm going to do here is I'm going to take, we need the actual IP. So I'm going to take this list, and we're going to actually map it to what we actually have in our cluster. And the reason why I want to show you this is I want to make sure you understand how the routing will happen from the load balancer from the outside that we end up creating. So we're going to take the hello service. What we're going to do, I'm going to delete it first before I add it back. So we're going to give it an array of public IPs. So what this means is create IP tables rules that says anything came looking for this destination, go through the process. So we can use the IPs of the nodes themselves. So then when I go and make that attempt to the actual node, it's going to hit IP tables and says, oh, you're destined for this particular node. I'll take over and route you over here. So we're going to do this now. We're going to throw this public service in, and it's going to be on this particular port. All right? So let's get the actual IPs for our service. So it's going to be, and this is going to be a bit tricky because you got to remember the public IP that you get from most of the cloud providers is not what's bound on your interface. And when you hit the public IP, it's not the thing that shows up in IP tables or shows up to the host. It's actually the IP that you see there. So you can't put the public IP. You got to put the thing that's on the host because it's just like, I want to say natting, but it's like the forwarding rule that they have in place. So you can really throw yourself off if you assume that you can use the public IP. So you can use the private IP that's on the node. All right, so compute, list, instances. All right, so what we're going to do, we're going to add, I'm just going to add 2 of these. So I'm going to use this IP. All right, so here's the kube 1, 0. So let's adjust our list a little bit here. The Power of M user is like, man, there's like macros to delete that whole line here. What are you doing, man? I'm leaving. I can't watch this anymore. Guy can't use Vim, man. He's copying and pasting, using the mouse. Ugh. All right. So I'm going to delete the service now. Get services. All right, kubectl delete services hello stable. All right, so we deleted the stable service, and then we'll just create it again. So create. And then we'll do the hello stable service. All right, so now we have the service. So now when we list our services, we get a list of public IPs that will be added to IP tables now. So in your load balancer, you would just put this select set of nodes behind it and say, this is the backend for this particular service. And they're the ones allowed to route traffic. Because you have 1,000 nodes, you're going to put all 1,000 in the backend for every load balancer that you have, right? So, and you also might be using node selectors to limit where the pods can actually run in a cluster. And this gets all automated for you, actually. So if you're using like a cloud provider, anytime you add a service, it automatically starts hooking up the load balancers if you're using it, right? This is all automated. I'm just showing you the manual way so you can actually get a feel for it. So this means that if anything comes into the cluster on these ports, it's going to do the right thing. So now we can try it. So now what we can do is, man, this better work too. All right, so now what I should do is be able to hit this public IP here. And I should get the port, and I should see hello, right? Let's see if we get that. Hello, right? So what's happening here is that I open the firewall rule for my whole network inside of GCE, so it's going to allow traffic into that cluster on port 80. Now, when I come in on this public IP address that's routable on the public internet, it's going to hit Google's networking stuff, their SDN, and it's going to say, oh, that IP really belongs to this particular instance. And what it does is it does manipulate the packet a bit, so it actually is coming from, or it's actually destined for the actual instance itself. So if we were to put this IP address in the mix, it wouldn't work. IP tables doesn't see that IP ever, right? It's decoupled from the instance. IP tables will only see the destination of the interface of the instance itself. And that's why we used it, and it actually works. So now we can actually hit these, and this is how you get outside the cluster. Now this seems like overkill and too much overhead. But if you notice something here, all of this is decoupled from the pods themselves. They're unaware of this. They can move around. They can live on different machines. And if you think about the default setup, you can hit any machines in the cluster. We can restrict what machines you can hit in the cluster. And we can allow all this routing to take place without anyone knowing where anything lives. And the goal is that this will scale pretty large. Mental overhead, you just don't think about it. You add the service. If you want to scope it, you scope it with public IPs. If you want to have every machine be accessible via the outside world, you can use a node port. So instead of me using the IP address like we did here, I would just say 104.38,000, and that would hit the hello service. We add a new service, 38,001, we hit the other service. you have options how you get data into this traffic, into the cluster. And if you're in the cluster and you have like an F5 or a Juniper router, you can do something even easier and just say, look, anything going for this /24 like we saw, goes to that host. That's the next hop. And then you get automated mix of all of this stuff. So it depends on your level, depends on your performance requirements. This is how the networking model works. And you're free to manipulate that service entry however you want. You can add and remove things. And the cloud providers in Kubernetes actually do this for you. So you add new backends to a service and you want to add it, it adds it to its internal representation, which then fires off to cloud APIs to start configuring your load balancers for you automatically. A machine dies, it removes it, right? It can do all these things dynamically because the APIs are exposed. And that's called a cloud provider in the Kubernetes sense. So you can imagine people building a cloud provider for bare metal environments, right? Where the router happens to be, or the load balance happens to be an F5. The storage thing happens to be a NetApp. In the cloud, these are better defined as like ELBs or GCE load balances and persistent volumes. And those just kind of work because the code's already written. But it's pluggable and you can build your own. But that's how you actually get stuff in and out of the cluster. The last part that we're going to do, and we're going to finish up a little bit early, I'm going to do the rolling update. This gets people like a bit excited because updating is hard, right? Like I've seen update scripts and they're hard because you have to know where things are. That's the hardest part about updating things. You have to know where they are. And that's again the database that we use, right? Excel or wherever you use. That database needs to have accurate representation where things are. So when things move because of a change window, and then it's like you had an emergency, you had to put it up, and then now the scripts don't work because that thing's no longer on that machine. So what we're going to try to do is use the APIs to do two patterns. One is the Canary pattern. How many people have heard or used the Canary pattern? Good. For the rest of you, the idea with the Canary pattern is that we have like something we sacrifice, and it goes in the coal mine first, and if it dies, we shouldn't go in there. It didn't come back, right? They don't do that. So what we want to do is like, look, your development teams wrote version 2 of the app, and you're like, I don't know if we should just replace version 1 with version 2. Like, you guys aren't really trustworthy in the past. So what we're going to do is we're going to like deploy one instance of version 2, right? We got 18 of version 1, and we're making money, and paychecks still flow. And I don't want to disrupt that process. So what we're going to do is going to give you one instance of the Canary, and then we'll see what that looks like. So we have a lot of these. So I don't know, we'll just do, now that we have that VIP, what we're going to do now is we're just going to like do a curl and see what happens when we start doing this Canary pattern. Actually, we have too many nodes, so I don't want this to take too long. So what I'm going to do is resize. So let's resize from 18 to something reasonable, like 3. All right, so we resize. So what should happen now is like kubectl get pods reasonable now. And this happens relatively fast because we say kubelet, hey, stop all that. Clean it up. Containers get deleted, and then the kubelet actually does garbage collection on Docker. So like you use up and down with these containers, and then you run out of disk space. The kubelet is a bit smart and say, well, no one's referencing these things anymore. All the pods get unique IDs, and over time it just does garbage collection for you. Right? So it owns Docker at that point. So now we only have 3. We're back to sanity. And even though we went down to 3, this still works. Right? We don't have to worry about updating anything else because we're using the VIP and we have our labels. So let's just watch this thing on the command line so it can be a little bit easier to hit. We're going to make one request at a time. So we'll do what is this? Wow, true. Do curl this thing, and then we'll sleep for a second. We'll sleep for 1 second, and then we'll be done. All right, good. So what's happening here? Wow. Oh, that's not good. We can't see that. So what we'll do, and then we'll just do what? How do you do this? Echo? My bash scripters are in the building. All right, so we're hitting the service. And the reason why I'm doing this one connection at a time is because I don't want any session affinity to pin me to a particular machine. I want to make a new request so I can be subject to round robin. So I'm round robining now. We're hitting one of the 3 nodes. So now it's time for the Canary pattern. And what we want to do here is we're going to send out a new replication controller that's going to look and monitor a specific set of labels, so not to confuse itself with the other controller. And the way we do this is, so let's look at that really quick. So this controller looks exactly the same as the other controller, has one replica that's all I want right now, but its label is a little bit different. The other one was looking for track stable. This one is looking for track Canary. So this controller won't look and touch the other ones that have track stable, right? And another thing, if you guys haven't realized from this label system, let's say like you guys are reporting issues in production, you can go on the pod and on the command line and remove a label, and then it will come out of the load balancer pool. It will be ignored by the replication controller, and a new one will be replaced, and now you can go log into that pod and deal with it and troubleshoot and look at logs, and then delete it on your own leisure. So you have the ability to play with these dynamically. So this guy is going to spin up a new pod with this template. But the only thing different here really is that we have a new image version 2 of Hello. And it's going to get those labels, and it's going to watch those, ignoring the other ones because the labels don't match. So kubectl create-f. I think this is hello. You can type Canary. And I'm using a controller here because I just wanted to make sure that the state stays the same. So I want 3 of stable, 1 of the Canary. And if this works well, we should start. Oh, well, we have to wait till it gets scheduled and goes through the whole thing. We got to pull from the Docker Hub. So kubectl get pods. Sweet. And somewhere in here, you see it? Man, you're just paying attention. I like it. All right, cool. So we see 2.0 popping in, right? And it joins the backend when it's marked healthy. So since everything's decoupled, the kubelet is like, all right, you want me to run the pod. There was a lucky winner somewhere in the scheduling decision. It wins, it spins up the pod, and then it gets marked healthy once it's actually running. And one thing I'm not showing here, there is lifecycle hooks for your pods. You can say, look, when you're being created, do this. Here's how you check my health status. Here's when I shut down, I want you to, this is how you clean me up. So you can actually specify different hooks in the lifecycle. So that way, the kubelet can really know that you're ready by saying, well, you want me to hit an endpoint on your app? I can do that for you. And then you're ready. Right now, we're just relying on Docker saying it's up and running. So now that it's up and running, it's marked healthy. So every label query now only shows the healthy pods. If this pod was marked unhealthy, the next request won't ever go to that pod. So now we're pretty happy. We're not losing any traffic. Things look stable here. We have a couple of choices. We can like scale up the other replication controller and go to 2, and we can see a mix of traffic. But let's just say, you know what, that's good enough. We're ready to go ahead to roll the entire cluster. So we're doing that now. So what I want to do now is going to roll the cluster. And this, someone asked a question about like, how do you update these in place? So before we did use like this patching mechanism where we'd say, look, take the existing controller and patch the image. And then what will happen behind the scenes would be you will create a new replication controller temporarily, delete this other one and rename it to this other one, and then it would just work for you, right? And I think we're still going to continue to do something like that in place, but one thing you could do is just basically say, replace one controller with another, right? And say like, here's how you stage it up. So this kubectl command behind the scenes is just orchestrating all the API calls, create this new controller with 0, and then spin this down. So -1, +1, -1, +1. Until you have all the pods moved over to 2.0. So we're going to try to do that now. So now we run this command. I'm going to do a rolling update with a grace period of 3 seconds. For production, you guys probably want to do a little bit more to make sure you have enough time for this thing to shut down properly before you roll to the next one. And then we want to do this to the stable controller at V1. And the V2 controller, even though we didn't look at it, it just has the V2 of the image like the Canary does. A lot of people ask me this question, and I'm going to show it because, do I have it? Normally people ask, like, what if I have a customer that I need to always have go to version 2 in this Canary model? I just want a set of customers to always hit version 2 no matter what. And the way you would do it, and I think we have time to do it, so we'll do hello, we'll just copy the hello service. Let's just look at it for the sake of time. So in our hello service pod, what we would do is, where's our service? So in our service here, what we would do is just adjust the labels. We would just add track equals Canary. And then that and then this, the new proxy that we make would only ever proxy traffic for the V2 controller that matches those labels, right? So you can just add another service here with track equals Canary, and then it would only ever have the results of this pod query to that one pod that matches. So you can add as many of these things as you want. All right, so let's go ahead and roll the cluster now. So as you're rolling the cluster, it just starts printing out things that it's doing. You know, it's bumping down the replica set, letting the replication controller kill a pod, saying you don't need it anymore. And since the replica state is down from 2 to 3, or from 3 to 2, it's not going to ever spin another one up. So it's just going to roll through this until we're completely done. And as it's making its progress, we should start seeing more traffic hitting 2.0. So as those things are being marked healthy, they become the backends inside of the controller. And if you're doing well-defined lifecycle hooks, you can make sure that your apps are shutting down gracefully and not dropping any traffic on the floor. And you'll see some of these pause because it tried a backend and it wasn't there, and it holds the connection at the proxy and then gets you to one that is. And it's a very simple algorithm that it's using. You can imagine it being more powerful in the future. So at this point, all the traffic is now on 2.0. And if we look at the controller, it's finished here. And there's tons of events that are firing at the system as this is progressing, right? We're done with the demo and tutorial, and you can actually follow these steps. So I try to do my best to copy and paste these things, and it will work on your own setup if you follow through this. Let's take a break. Happy to come back for questions, and thank you guys for attending.